We're going to talk about two-dimensional vectors. So first, a couple of definitions. What is a vector? A vector is a quantity that has both a magnitude and a direction. And this is opposed to a scalar, which is a quantity that only has a magnitude. When we talk about magnitude and direction, what those things mean is the magnitude is just the number associated with it. So if I say 10 seconds have passed, that means the magnitude of that number, that quantity is 10 seconds. If I say I'm going 10 miles per hour north, the magnitude associated with that number is 10 miles per hour. Okay, so examples of vectors include things like force, because a force has a magnitude, I push with 10 newtons, but it also has a direction, I push in a certain direction. Force, momentum is another one. Another one people mess up a lot is velocity is a vector. So velocity is what I just said, 10 miles per hour north, and that's as opposed to speed, where speed is just 10 miles per hour. You only care how fast, not in what direction. Okay. Scalar quantity with only magnitude. Temperature, right? Temperature only has a number, it doesn't have a direction. Time. Time is one that sometimes people think is a vector because we talk about the flow of time being in a certain direction. But vectors, we're really talking about spatial directions here, and time obviously doesn't have a spatial dimension. So yeah, temperature, time, speed are all scalars. Force, momentum, velocity, vectors. Magnitude is the length of a vector, which you can see we're going to show you in a second, because we're going to actually sketch some vectors and draw what they look like. And then we're going to be using the terms vector components a lot. Vector components are going to be the part of a vector that points purely in a given direction, typically x and y. So often when we want to draw a vector, we draw it as an arrow, okay, where the length of the arrow represents its magnitude. So this is the magnitude. So a larger vector, longer arrow, has a larger magnitude. And for the direction, we typically measure it relative to the horizontal. So this, I'd call this some theta here, and this would be my direction. This isn't always true. Sometimes if you're doing something with like bearings, you say, oh, I'm going 20 degrees east of north, right? And then if I say, okay, well, this is north up here, and if I'm going east of north, then I'm going to say that this is my angle theta. So this is going to be 20 degrees here if I go 20 degrees east of north. Okay, so always make sure you pay attention to what direction is being measured relative to. So we can add vectors, we can do operations with vectors, they're mathematical objects, just like we can do with scalars. You guys have learned in the past how to add and multiply and divide and do all these things with scalars. Now we're going to talk about how to do some of these same things with vectors. So for 2D vectors, really we're just going to be adding. Multiplication has an analog with vectors. Actually, it's two analogs with vectors, but those are going to come in with 3D vectors. For now, with 2D, we're just going to add and subtract. So if I have two vectors, let's say I have a vector A that points like this, and I have a little vector B that points like this. If I want to add these two vectors together, a vector plus a vector is going to give me a vector. So if I do that plus that, the way this is going to look is I add them tail to tip. So I draw my first vector A, and it is commutative. I could draw B first and I get the same thing. And then I draw B down like this. And then I get my resultant vector. The resultant vector is my answer, right? So my resultant vector, it looks like this. And you can see that if I were to change the order that I add these in, right? If I do this first, take this vector B, and then add A tail to tip, and I do this, that's probably not quite right. Try to make it more accurate. Let's say that's it. Then my resultant vector is the same thing. Now, vectors do not have they don't have to begin at a certain point or end at a certain point. The only properties that vectors have is length and direction. And so if I draw a vector here that has some length and direction, and I draw some vector here that has that same length and direction, these two things are the same vector. Because there's no special starting point or ending point. They just have a length, they have a direction, that's it. So now we're going to look at how to do stuff with vectors when we're looking for more exact answers and not just for sketches. So if I have a vector V, like this, with an angle of theta relative to the horizontal, I often, and you'll see why in a second when we do the example problem, but what I'm going to want to do is it's hard to work with a vector that's pointing in an arbitrary direction. And so what we're going to want to do is we're going to want to break it into two vectors, one that points along the x direction and one that points along the y direction purely. This makes a nice right triangle. Because once it's in the x and the y direction, then we don't even really have to worry about the angle, right? I can just do stuff with all my x terms, do stuff with all my y terms. And these vectors, what we're doing is we're applying graphical addition, right? But just kind of in reverse. Where if I said this vector here is vector A, and this vector here is vector B, what's their sum? V would be the resultant vector. So this is like reverse addition, where I'm saying instead I'm going to take this vector V here, and I'm looking for two special vectors that add to this. And the two vectors that add to this are going to point purely in the x direction and the y direction. And that's what my x and y components are. And so this bottom one I call Vx. And this is going to be equal to, in this particular case where my theta is drawn, V cosine theta. And Vy is going to be equal to V sine theta. And those are their magnitudes, right? Their directions are purely to the right and purely up. And now I have a couple of ways of representing this as like one vector. One way is with this bracketed notation that looks a little bit like matrices. And that's not a mistake. Also, this little hat over the vector just helps to distinguish this from a scalar. If you see the little hat over it, sometimes you'll see in textbooks people will draw little arrows or they will bold the term, the letter. That also means vector as well. So you can write it like this, right? Write my x component on top and my y component on the bottom. This is always the arrangement. If you see a number on top, number on bottom, x is always on top. Okay, and then when we do 3D, you'll introduce a z component on all the way at the bottom. And so in this case, it would be equal to v cosine theta, v sine theta. Okay, and this is complete information about the vector v. If I'm given its components, I know everything there is to know about it. And if I want its magnitude, I can find it. You can probably guess how, but we'll go through it in a little bit. Okay, this is not the only way to write a vector in terms of its components. I can also write the vector v as a sum of vx times I hat plus vy times j hat. What are I hat and j hat? They're called unit vectors. Unit vectors are vectors that are length 1. Okay, and these I hat and j hat vectors are very special unit vectors because I hat points entirely in the x direction. So it is the vector 1, 0. J hat points entirely in the y direction. So 0, 1. Okay. And so these numbers, if I multiply a vector by a scalar, right? If I do put a 2 here and I multiply 2 times this, it's going to generate the vector 2, 0. Same kind of property as we did with matrices earlier in the year. So here, this is going to be, I can go back and forth between these two forms because they're equivalent. So this would be v cosine theta I hat plus v sine theta j hat. And then, if I wanted to, I could say, oh, well, I hat is 1, 0. So if I multiply that in, I get v cosine theta 0 plus 0 v sine theta. And the way you add vectors in component form like this is you add all the components that are in the same spot, basically, right? Add all the x components together, add all the y components together. So then this gives me this vector over here, right? Because v cos theta plus 0 is v cos theta, 0 plus v sine theta is v sine theta. And so that's how we can express a vector in terms of its components and still have a complete picture of that vector. Okay, so let's look at doing a problem with vectors and how we would apply these notations. So I'm going to say that we have some random object, and it's just kind of floating in space or whatever. And I'm going to have one force that pushes on this object or pulls on it. It's going to be 10 newtons. When I say newtons, Newton is just a unit of force. So it's pushing on it 10 newtons at an angle of 45 degrees. And let's say there's another vector, another force acting on this object. And I guess I should try to represent what I'm actually drawing here. So this one's going to be at an angle of 30 degrees. And technically it should be half as long because it's 5 newtons. But, oh well. And then this is a 30-degree angle here. And what I want to do is I want to find the net force. Find the net force and the direction of that force. Okay? Because basically if, these two forces are pulling on this object, we can just add all the forces together and treat it as one force acting in some other direction. So how do we do that? Well, first, we're going to want to split all of these vectors into components, because random vectors pointing in random directions, we can't do anything with them. We can't add them in any kind of useful way. But we showed earlier that if I split it into an x and a y component, then I can add all the x components together and I can add all the y components together. And that seems like a good place to start. So if I split this vector into an x and a y component, the 5 Newton vector, let's call this one v1, and this one over here v2. So v1, this is going to be equal to, on this side, the y component up is going to be of magnitude 5 halves, right? Because I'm doing sine of 30 degrees, 5 times sine of 30 degrees. Sine of 30 degrees is 1/2 times 5 newtons is 5 halves newtons. So 2.5 newtons. Then I'm going to have an x component that points to the left. And this x component is going to be 5√3/2 newtons. Right, we're just doing 5 times the cosine of 30 degrees. So now I have an x component and I have a y component for my first vector v1. So vx1 and vy1. Now I'm going to do the same thing for this vector. And this one, both sine and cosine of 45 degrees is √2/2. So 10√2/2 is just going to be 5√2. So I can write this as one vector like this, where vx2 is 5√2. And vy2 is equal to 5√2 as well. And the units are newtons, of course. And so now I'm going to write this in bracket notation, but you're certainly welcome to write it however you want. I'm going to try to add vector v1 plus vector v2. And we have to be careful of one thing here. So when I'm writing vector v1, this certainly is its magnitude, right? 5√3/2. But I do have to actually incorporate the direction here. And this vector points to the left. And as a default, right, I'm going to choose right to be positive and up to be positive, and then left and down are going to be negative. So I have to actually write here that I have negative 5√3/2 newtons is my x component of vector 1. And the y component is going to be 5 halves newtons. And I'm going to add that to the x and y components of vector 2, which are going to be 5√2 newtons, 5√2 newtons. And if I weren't doing an operation with this vector on the right, v2, and I were just writing this as like a final answer to something, you do want to simplify this as much as you can. And the way you would simplify this is you'd factor out this 5√2. So you'd have like 5√2 newtons times the vector 1, 1. Okay, just like a nice, neater way to write this vector out. But because I'm adding these together, I want to be able to see actually what I'm adding together, so I put it in here. So then this is going to be equal to the vector negative 5√3/2 newtons plus 5√2 newtons as the x component. And the y component is going to be 5 halves newtons plus 5√2 newtons. Okay, and there we go. I summed the vectors. But this doesn't tell me what I was actually trying to find. It doesn't give me the answer I'm looking for. I wanted the net force and direction. So I'm looking for a magnitude and a direction. And what I found instead is I found the x and the y components of my net force. So how do I go from component form back into this form where I have a magnitude and a direction? And you could probably guess, but what we're doing here is, well, I say I have two sides, so I can add them graphically to get the resultant vector. And the way we do that is, hey, look, it's a right triangle, Pythagorean theorem. So now that's what we're going to do, is I'm going to find the magnitude of v1 plus v2. And these double bars on each side, in some textbooks you'll see single bars. I like to use double to differentiate it from just, absolute value of a scalar. But we want to take the magnitude of the sum of these vectors. So that's going to be equal to the square root of the x component squared plus the y component squared, right? This is my x component of my resultant vector. This is the y component of my resultant vector, Okay, so I'm going to have negative 5 root 3 over 2 newtons plus 5 root 2 newtons squared plus 5 halves newtons plus 5 root 2 newtons squared. And I'll put this in a calculator. And when I do, I get that my magnitude of my resultant vector is about 9.9558 newtons. Okay, so this is good. This is a good start. This is the magnitude of my resultant force. But to really complete this, I need to know what direction it's pointing in, because the resultant force that points to the left is very different than a resultant force that points to the right. It's going to give rise to very different behavior in the object. So how do I find this angle theta that I want that makes these two vectors make, right? Because I have some Vx, Vy, and I've just found the magnitude. I found this, and now I want to find this. So to do that, we use more trig. I say that theta is equal to the arctan of the y component of my vector divided by the x component of my vector. And so the vector that I'm interested in is this net force vector. So the y component is going to be 5 halves newtons. I guess I should write that I'm doing the arctan here. So I have arctan of 5 halves newtons plus 5 root 2 newtons divided by negative 5 root 3 over 2 newtons plus 5 root 2 newtons. And when I put this in a calculator, I get about 74.019 degrees. And when you do this, it's always good. You always want to make sure you're in the right quadrant, right? And here I know that my sine, right? So if I do this out, my sine should be positive and my cosine should also be positive. And so 74 degrees is in fact in quadrant 1, so we're good. Okay. And now I have my answer. Basically, this gives me a force. So I had a force like this, and I had another force like this that was weaker, and this results in a force that points around here, right? 75 degrees, approximately 74 degrees, with a 9 newtons of force. So that makes sense, right? It's kind of an average of these two. That's essentially what you're doing. And also just make sure that your answer makes sense, right? So aside from checking the quadrant, you can do that mathematically, right? And say, well, where should sine be positive? Where should cosine be positive, or whatnot? But you also want to look and say, well, if I'm adding two forces like this, these both have positive y components, and that means that I should never ever find them in the negative quadrant, right? Because I can't take two positive forces, add them together, and get a negative force. Or that's true for any vector. Two positive vectors can never equal a negative vector. And that's it. That's how we do this kind of problem. So here, right, we want to add two vectors together that are not in component form. We convert them to component form, sum them in component form, and then once we've done that, we convert it back into the kind of general form here. So here I could say, for my final answer, I would say, oh, there's a net force of about 10 newtons at an angle of 74 degrees. Okay. So to summarize, because I want to just leave you with a nice summary of all the key takeaways here. So for vectors, the magnitude of a vector is equal to the sum, the square root of the sum of the squares of its components, right? And this is just trig. If you just draw a picture, a triangle of this, you should be good. The angle that a vector is going to point at is equal to the arctan of the y component over the x component. Also, just geometry comes from that same triangle. Also, if I have a vector that I'm starting with and I want to find the x component of that vector, it's equal to v times cosine of theta, and the y component of the vector is v times sine theta. If you've previously watched the videos on polar, you're going to notice that these are identical to the conversions between polar and Cartesian, which should make sense because it's literally the same triangle that you're drawing here. The only difference here, right, is that you have to remember that these have kind of a directionality to them. The x component, the y component have a direction. The magnitude is just a number, right? A vector has a magnitude and a direction. So the magnitude of a vector will always be positive. Direction, can be anywhere between 0 and 2 pi or 0 and 360. So that's it. That's two-dimensional vectors. Thanks for watching.